Hello and welcome to today's lesson on proportional confidence intervals. As you can see, our objective for today is by the end of this lesson, I will understand how to construct a proportional confidence interval and why they are important in statistics. Okay, now the why. Why would we want to construct proportional confidence intervals? Proportional polling is probably one of the most common statistics you see in TV or on the internet when referring to anything from the president's approval rating to what percent of people choose Jif over Skippy. Okay, so we're going to look at one situation here that I just pulled off of the internet, and our poll question that we're going to look at is college worth the cost? Okay, so we had a national research center that went through and did some surveying, and we'll look at their information and use that to build some of our intervals that we'll work with today. Okay, now as we go through this process, before we start, we want to understand, is the answer that we get something that we can trust? And that's where our assumptions or conditions come into play. So we always want to test our assumptions, our conditions, to make sure that the answer that we get is something that we can trust and we know is valid overall. Now, if it fails an assumption or condition, we don't stop. We just have to understand that we might not be able to trust the value that we get as much as we would want to overall. So when we look at the situation, and here's the situation describing how the information was collected. So the first thing that we want to verify is, do we have a random sample? Okay, in this problem they talk about a representative sample, okay, but the random sample is not stated in the problem. Okay, so we would want to write that random sample, not stated in problem. Okay, a representative sample could be random, but since it's not stated specifically, we would want to be careful with using that term. Okay, the next thing that we look at is the independence of our sample. Is our sample small enough so that it would be independent from any other sample that was collected? And if you remember, our independence formula is 10 times the sample size. Is that less than the population? So if we look at our sample size, and here it's an approximate sample because it's a very large sample overall, sample size of 29,000 times 10, okay, equals 290,000 overall. And what we have to decide is that less than our population? Okay, so the population that we're looking at is college alumni. Okay, so are there more than 290,000 people that have graduated college? Yes. Okay, so we do know that it is independent. Okay, and then the last part is, do we have a normal sampling distribution? And this goes back to our sampling distribution unit, and what we have to be careful of here is we can't just say n is greater than 30 and we're done. When we're dealing with proportional distributions, and if you remember back to our unit, we had to test n times p, n times 1 minus p, and show that both of those were greater than or equal to 10. Okay, and based on that size, we know that we can verify that we're dealing with a normal sampling distribution. Okay, now, our proportional value that we work with, I'll give you that in a second because we'll see that later on in our problem. But our sample size, 29,000, times our proportional value is 0.47. Okay, so we multiply that out. Is that greater than or equal to 10? Yes. Okay, and then we look at 29,000 times 1 minus 0.47. Is that greater than or equal to 10? Yes, that is as well. Okay, remember, you have to show the work to verify these assumptions. Okay, so now we know that we're dealing with a normally distributed population. We have an independent sample based on size, and we're just not sure if we have a random sample based on the way the question was stated. Okay, so now when we look at the calculations, okay, they have it broke down into different categories, and we're going to look at one category right now. But what they did is they asked the question, my education from whatever the stated university was worth the cost. And people could agree, strongly disagree, strongly disagree, or have a neutral statement. So in this situation, we're looking at the strongly agree proportion of individuals. Okay, so we're going to look at the private nonprofit individual, and we can see that of this sample, 47% of these individuals agreed that it was worth the cost. And what we want to remember is this 0.47 is a sample, okay, so we can put it on a distribution, but we know this isn't probably the perfect value for the population overall. So what we need to do is we need to stretch out in both directions, create an interval worth of values that will have a good chance of capturing the true proportion for the overall population of college graduates. Okay, so if we look at our formula, and this is the formula straight off of the formula sheet that AP gives you. Statistic plus or minus critical value times standard deviation of the statistic. Okay, since we're dealing with proportions, we're going back to our p-hat value, which is our sample proportion or statistical value. Our standard deviation formula comes from the formula sheet. Okay, we also used it back in our sampling distribution unit. And then now notice when we're dealing with proportional values, we're going to use a z-star instead of a t-star value. Okay, so let's go through the process to build a 95% confidence interval for the private nonprofit university group. Okay, so now we know our statistics, central value 0.47, plus or minus our z-star, which we'll find that in a second. Okay, and then we have our standard deviation of our sample, 0.47 times 1 minus 0.47, all divided by our sample size of 29,000. Okay, now, if we want to find our z-star value, we do the same thing that we did, and we actually pull up the t-distribution table. Okay, remember, this table is the quickest way to find the critical values for a confidence interval, okay, because our confidence level is listed across the bottom. We're finding 95, and when we're dealing with a z distribution instead of a t distribution, okay, we work to the infinity value for degrees of freedom, because when we're dealing with z's instead of t's, okay, we don't use degrees of freedom. Okay, we're working off of that true z value of 1.96. Okay, so we can put that piece in. Okay, now from here, all we do is we run our calculation. Okay, find our two interval values and our lower boundary, 46.4, our upper boundary, 47.6%. Okay, so we have our two proportional values, and you can see based on this sample size, okay, the value doesn't move much overall. Okay, so we know this is a pretty good estimate of the true population of the overall value. Okay, so now how do we finish this up? Okay, we've gone through our process, we've tested assumptions, we've done our calculations, and now we need to write our conclusion. Okay, remember, your confidence interval conclusion needs three things: confidence level, the interval that you created, and then the context of the situation. so if we look at our answer here, okay, we are 95% confident that the true proportion of all alumni that attended private, nonprofit college and university and thought it was worth the cost is between 0.46 and 0.47. Okay, so we're looking at that interval, gives us the range of values. Okay, if a person was reading this conclusion, they would know exactly what you did and what your solution was. Okay, now, what else can we do with confidence intervals? Okay, one thing that we always look at, and it's always listed on the TV, is they always talk about the margin of error. You know, when they give the president's approval rating, they always say that this approval rating has a margin of error of plus or minus 3%. Okay, so we want to know if we want to be specifically accurate. Okay, you know, we want to be as accurate as possible. We want to make sure there's not a huge swing in the percentages. Okay, what we want to do is we want to look at our margin of error, and we're only working with this portion of the formula. We don't know what the central value is. We just want to look at the accuracy of our answer. So let's look at this situation here. If we want to be 99% confident that whatever value we get for a proportion is within 2% of the true proportional value, okay, we can find out how big of a sample do we have to collect in order to make this happen. So now we start building based on the formula. We have our margin of error, 2%, 0.02, equals our z value comes from the confidence level. So if we want to be 99% confident, we go to our t-table. Okay, the t-table gives us the confidence levels at the bottom. Okay, 99% means that we're 2.576 standard deviations in either direction will give us that 99% confidence that we're looking at. Okay, and then we have the rest of our formula, standard deviation of our sample. And we're solving for the n value. So now, if we're solving for n in this situation, there's one problem. We don't know what p is. Okay, so p is a question mark value. Okay, so now we have to figure out what type of p-value would we use to give us the best situation possible. So let's start looking at what would happen in this part of the formula with different p's. Okay, if p is 0.9, 1 minus p is 0.1, we multiply together and we get 0.09 for that numerator value. If p is 0.7, 1 minus p is 0.3, we get 0.21 for the numerator value. If p is 0.5, 1 minus p is 0.5, we get 0.25. Okay, now remember our goal here is to make sure that we're getting the appropriate sample size for this situation. And what we want to do, since we don't know which one it is, we don't know out of these three which one we would pull or which one is the true value closer to, we want to give ourselves as much room for error as possible and just work with 0.5, 0.5 for our p-values. So now we can substitute that piece in. 0.02 equals 2.576 times our standard error. P times 1 minus p is 0.25 over n. And now from here, we're going to start working through to get our solution. Okay, now these values are going to get really small, so I'm going to jump over to the calculator and show as we go through this process. We want to do our solving steps. So the first thing we have to do is clear off our multiplier. So we need to have 0.02 divided by 2.576. Okay, and we get 0.00776. So you can see this value is getting small very quickly overall. Okay, so we've got 0.0076 0.776 equals the square root of 0.25 over n. Okay, now we're solving, so we're using the undoing steps. How do we undo a square root? We have to square both sides. Okay, and you can see we're dealing with some extremely small scientific notation values, 0.0000603, okay, to 3 significant figures. And now I'm just going to put that over 1 so I can cross multiply and solve. So I now have 0.25 equals 0.0000603 times n. Okay, or I'll work just within the calculator and know that I need to take 0.25 and divide it by the answer that I had previously, okay, to get my n value. Okay, now remember, this is a mathematical answer. Remember, we can't have 0.36 of an individual. Okay, so in this case, we are always going to round up to that next person. Okay, so we would have to sample at least 4,148 to make sure that our margin of error was within 2% at 99% confidence. Okay, so now for wrapping up, we've got our Schoology quiz at the end of this lesson, and also for the extra practice, the in-class packet that was placed at the beginning of the unit. If you want to work on and do some more problems of this type, the margin of error and confidence interval questions are built into question 1 and 2. Thank you and have a good day.